Hello, everyone. Hope you all had a nice weekend. Excited to be back here doing physics, yes? You just say no.
I was feeling fun.
Oh, gosh. No was funnier. Anyways. Got some more people coming in. We're not quite full yet. Anybody have any questions before we get started?
Yes, but I have to wait till after class to ask you them, please.
Okay, no problem. This
What
is
chapter are we
Tristan.
on?
We're on chapter
Yes.
10.
Yeah,
In
I'm in
fact,
the same boat.
we should be finishing chapter 10 today, and y'all have, of course, the concept y'all could be doing already, but they're due, I think, Wednesday, and then the actual homework's due on Sunday.
You said the conceptual for chapter 10 is due this Wednesday?
I believe it's due, yeah, tomorrow night.
Okay.
I would check it and make sure, but yeah, that's what I seem to recall. I fixed everything up through, I think, chapter 11. I think everything up through chapter 11 is fixed now. That means 10, 36, and 11. All right, well, we got 11 people. I guess that's how many we're going to go with. Anybody have any questions on course material or anything? I got an announcement I'm going to make too, but I want to make sure y'all don't have any questions before I get sidetrack you or whatever. All right, well, here's the big announcement. So I've had a lot of people asking me about the midterm. I know a lot of people did poorly. I know a lot of people did worse than they're used to doing on tests, and that's what I've sort of been warning you guys about the whole time. Not to say that you did something wrong. I'm just saying this is what happens every semester. So it's really easy when I'm giving you practice tests and then giving you online tests where you're allowed to use your notes and your book and Google and all that stuff. It's easy to not recognize how much use you make of those notes and the book and the Google and the internet and all that good stuff. And usually the first time people figure that out is on the midterm. So that's part of the reason that the midterm grade is so average is normally so low. Now we had people that made 98, 95 or whatever in the midterm, but the average was quite low. And I would say even if you're in the low 50s, don't worry about it. It's not that big a deal. The reason why is this: automatically every semester, so don't tell your friends, but every semester when I do a midterm like this that's proctored as far as online classes, that midterm, if that's lower than your final exam grade, which is another proctored test, then I replace it with the final exam grade. So all you have to do is do better on the final, and if you do the level that you like on the final, then that's going to be what your midterm score is as well. So I do that automatically. You don't have to ask me. I just do it automatically. So that's why I'm not doing any kind of curving or anything on that midterm. The grade is what it is. I want y'all to be able to see the questions and stuff like that. And then, like I said, my final is comprehensive, but it often includes questions from previous tests. So questions that you've had on previous tests, as well as the midterm, are very likely to appear again on the final. So do your best on the final, and that can erase everything about your midterm. Anybody have any questions about that?
What if you did good on the midterm already?
Then you get to keep that grade, and I won't reverse the other way. Like if you do bad on the final, I don't do it the other way, because the final is really the big show, really. So the final is the one where you're supposed to peak. Your knowledge of this semester of physics should be at a maximum. Your knowledge and your ability at the day of the final exam. So I have to encourage that. But it does give you a nice buffer, so you can make, if you did really well in the midterm, it means you can screw up a little bit on the final, and it's not going to hurt you as bad. So, anything else? All right, well, let's get into chapter 10 then. We've been doing chapter 10, and I talked about how basically you had kinematics, which are exact parallels to the linear kinematics. X equals 1/2 at squared plus v0 t plus x0 turns into theta equals 1/2 alpha t squared plus omega 0 t plus theta 0, all that stuff. Well, what we're doing now is I'm wanting to show you some stuff about kinematics that needs to be pointed out. Like there's a vector associated with the angular velocity and there's a vector associated with the angular acceleration. Only it's a weird thing. It's not really a vector. So I got to parse that out for you. And then I'm going to start into using Newton's second law for rotation, which is really the summation of the torques is equal to I times alpha. So let's go ahead and start into that. I'm going to turn on my document cam. And remember, a lot of this information being parallel to the linear kinematics was partly because this equation from trig, S is equal to R times theta, which was really sort of a definition of the angle radian, the radian angle. If you take and realize this S is just like any parameter X, then you can say, well, V, the velocity is dx dt. But if R is a constant, that's just R times d theta dt. And we define this to be omega. Similarly, acceleration is dv dt, which if R is constant, that becomes R d omega dt. And we define this as alpha. Well, it turns out we can imagine, for instance, a disk rotating with angular velocity omega, rotating counterclockwise, say, and we can call this, or we can put a vector symbol on this and then represent it like a vector. And the way it works is this: you take your right hand, that's my right hand, you curl your fingers in the direction that the thing is rotating, and then your right thumb points in the direction of the angular velocity. So in this case, the angular velocity is coming out of the page. Okay. Now it's actually a pseudo tensor, a pseudo vector. PSEUDOVECTOR. And I'm telling you this for, you know, reasons that you that will become important later. Like you can't just add this to another vector and expect to get something that makes sense in the strictest sense. And the reason why it's a pseudo vector is it doesn't obey those rules that you learned in algebra. So depending on what kind of algebra class you had, you might have had a class that started with the rules, the commutative property, the distributive property, the multiplicative property of 1, the additive property of 0, distributive property A times B plus C, A times parentheses B plus C is equal to AB plus AC. That was another type of equation. Well, some algebra courses start off with that and then use that to make manipulations of existing equations, like, you know, 2x plus 3 equals 7. You could say, well, I could subtract 3 from both sides and this equation is still going to be valid. But using those little principles, you could learn how to solve equations. Other classes would teach you how to solve these equations, and then later on they'll teach you these rules. But the deal is those rules are rules that define what we call a vector space, and or an algebra is another word for it. So anything that obeys those rules are vectors, and you can't, you know, use the operations of addition, subtraction, multiplication, all that good stuff. You can't use those to get something that's not a vector if you're using vectors to begin with. Well, this omega doesn't fit those properties, so that's why it's not. That's why it's called a pseudo vector. And let me show you why. So let's imagine this is a mirror. Okay, and we draw a little particle with a velocity v, and then we look at its reflection, and v in the mirror both point the same way. That's good, right? Well, if you take that disk we just looked at, notice this side is this side, and that's the part of the disk that is farthest from the mirror. Then the omega pseudo vector points this way. Well, if you go and draw the reflection, remember the farthest part is this, so that farthest part is going to be coming up and going this way. Now, if you use the right-hand rule on that one, you'd see that omega points this way. So that is really a pseudo vector. Things that do that reverse their direction in a mirror are not true vectors. They're called pseudo vectors. So it's a little pedantic to point out, but it's something that'll come back as you do cross products and stuff like that. Remember, I told you right-handed coordinate systems and all that stuff. All that stuff is related to why this is important. So I'll leave it at that. That's your book also thought it was important to say, so I wanted to point it out that way. Now that we've done that, let's go ahead and review what torque is, and then I'm going to show you some nice examples of how to calculate torque. So torque, spelled T-O-R-Q-U-E, is given many forms. I gave you one form, torque is equal to R cross F, where R is like your lever arm, and it points from, that's lever arm, points from center of rotation to the point of application of the force F. Okay, so that's really what that R vector does. It points from the center of rotation. If you're putting torque on something, your intent is to rotate it. The center of that rotation, the axis of that rotation, is where the R vector starts, and the R vector ends on the location of the force. But you also know that the magnitude of torque is R times F times the sine of theta, where R and F are tail to tail. Okay. You also know from your understanding of the cross product that if you complete the parallelogram, it's the area inside of that parallelogram, and the right-hand rule dictates that the direction would be R. So this right here is acting like the vector R, so I can turn it any way I want to, but I have to turn it in such a way that my fingers can naturally curl towards F, which is this way. So now my fingers can curl towards F. Notice my thumb is now pointing into the page. So R cross F, the torque, would be into the page. So when you're using this type of thing, you're going to calculate the magnitude. You can actually figure out the direction from the right-hand rule, and that's just fine. But if you also look at this and say, hey, wait a second, this right here is a right angle. And of course, if I take F and multiply it by the, or excuse me, if I take R and multiply it by the sine of theta, which is that and that, then I get the component of R, or excuse me, the component of F that's perpendicular to R. So you can also write it as F perpendicular to R. Or you can do it the other way and take something that's perpendicular to F, say right here, break up R into that component and that component, then you get R perpendicular times F. All three of those, all four of those are ways you can calculate torque. And now I want to show you a couple examples and all three ways. Okay. So first off, let's do example one. Let's imagine a regular hex nut. One, two, three, 4, 5, 6, 7. That's a octagon. Well, anyways,
Can't see the.
thank you. I was just sitting here thinking, man, I just drew an octagon instead of a hexagon. But anyways, so let's imagine this wrench, and I'm going to idealize it like it's, perfectly thin little handle or something like that. But this is a real problem in that this nut is really on very strong, so it takes a huge torque. So I'm going to put what we call a breaker bar around it, and that's where you put something on it to extend its lever arm even more. So you can do it with like a steel pipe or something like that, stick that on the end. Sometimes you can take a wrench and stick it in the hole in the end of the wrench, and that'll give you a little extension. But in this case, the actual lever arm vector, maybe I'll draw it blue. The lever arm vector points from here to the point. It's not supposed to have that zag in it, but anyways, that's the lever arm vector. And it has, say, a force of 100.0 newtons acting at 36.9 degrees. Okay, notice this R vector pointing from the center of rotation to the point of application of the force. So the R vector is right. And in fact, in order to do the cross product with the proper sign, I'd have to put this vector tail to tail with that one. So it'd be like that. And you'd see it's, you know, you could do that. It's just not something you necessarily want to do. What I'm going to do instead is I'm going to realize that, hey, this vector right here, F, has a component, F perpendicular, that is perpendicular to the lever arm. And then it's got another component, F parallel, that's parallel to the lever arm. Okay. And I can realize that that's a very special angle, that 36.9. In fact, that special angle is 36.9 is part of a 3, 4, 5 triangle, and it's opposite the 3. This one's opposite. This one's the 4, and this one's the 5. Of course, to make 100 out of 5, I got to multiply it by 20 newtons. So I multiply this one by 20 newtons as well, and this one by 20 newtons as well. So I can see now that F perp is equal to 100 times, or excuse me, F perp is equal to 3 times 20, which is 60 newtons. Okay. And let's say R is actually 1.00 meters long in terms of its magnitude. So now I can say the torque is just going to be F perp times R, that's 60.0 newtons, times 1.00 meters, that's 60.0 Newton meters. Now, Newton meter is also a joule, but remember, we never use that fact when we're dealing with torques. We always do a unit of force times a unit of distance, like an inch pound or a foot pound or a Newton meter or a Newton centimeter or a dyne centimeter or something weird like that. Okay, so that's one way. So we've now seen, you know, how to use this version. You can just take the component of R that, or excuse me, the component of F that's perpendicular to R and solve it that way. Now, there's another example I can show you that I think is pretty helpful. And this is one where it's going to show you an actually R perp times F. So this will be example 2.
You need to scroll down.
Thank you, appreciate that. So what we're going to do is we're going to imagine that we've got a job at a sorority house. Okay. And this right here is 5.00 meters long. This right here is our pivot point. So in other words, we put a screw down right there at that corner, and we're going to be rotating this thing into place. This is going to go up, over, down, over, like this. This distance right here is going to be 2.50 meters. This distance right here is going to be 0.500 meters. This distance here and here is going to be 0.500 meters. And this distance right here is going to be 0.500 meters. Okay. Now, in addition to that, I am going to apply a force right here, F, whose magnitude is 100.0 newtons. Okay. It's horizontal, by the way. I've tried to draw it horizontal because I meant it to be horizontal. Okay. Just like these are all horizontal and vertical as well. Okay. Now, in principle, the R vector points from here to here. There's your R vector and there's your F vector right there. So you could actually do all the cross product stuff and all that. And I'll remind you how to do a cross product. But what I'm going to use is torque is equal to R perp times F. The reason being is that I see that from here to here is a component of R that's perpendicular to the F, and I can tell that component is going to be 5 plus 0.5 meters. So it'll be 5.50 meters. And then, of course, I just multiply it by the 100.0 newtons with that extra sig fig there. So in fact, that becomes 550.0 Newton meters. Okay, again, I could use my right hand rule, and R cross F should be pointing out of the page. Okay, so I'll write out of page. So let's check this. Let's actually see, does this work in terms of the cross product, you know, using the actual determinant stuff. So torque equals R cross F can be done by taking the determinant of a matrix I hat, J hat, and K hat being its first row, the second row being the components of R, so Rx, Ry, and Rz, and then the third row being the second vector, which would be Fx, Fy, Fz. So taking the determinant the way I taught you with, you know, you cover up this guy, and of course that's the 1, 1 element. So 1 plus 1 is 2, -1 to the 2 power is +1. So I just cover up this column and this row and take the determinant of the remaining matrix. So I'm going to write R, Y, F, Z minus R, Z, F, Y times I hat. Now the J one is 1, 2, and -1 to the 1 plus 2 power is -1 to the 3 power. So that gives me a negative. So this time I'm going to take my determinant backwards. That'll correct for the negative, but I cover up this column and this row. And normally that would leave this for my 2 by 2 matrix, but I'm going to do it in the opposite order. So I'll do RZ FX minus RX FZ, and that's in the J hat direction. And then finally, I do my K hat. Well, K hat is 1, 3. 1 plus 3 is 4. -1 to the 4 is +1. So I don't have to do anything weird, but I do have to cover up this column and this row. So I get RXFY minus RYFX. And that's K hat. So that's the way you can go about doing it. You can memorize this formula. You can work that out. Whatever you want to do is just fine. You can also see a pattern here. This is Y, Z, Z, Y, and then of course X. So notice all three of them have different directions, and these two are just the reverse. And that's the way it is on all of them. This is Z and X, and this is X and Z, and then this is Y, and this is X and Y and X, and then this is Z. So there's a lot of different ways to look at it. Now, what we're going to do is we're going to imagine that this is actually in a coordinate system such that the origin is the point of rotation. So there's the X, and there's my Y axis right there. Okay, so now I'm going to go ahead and form my R vector. My R vector is going to be, it's going to have an X component of, notice I go over here, from here to here is 2.5 meters, but that started 0.5 meters before the y-axis, so I need to subtract 5 meters from it. So I'll say, or 0.5 meters from it. So I'm going to say that's 2.00 meters in the I hat direction. And then this other one was 5.5, so it'd be plus 5.50 meters in the J hat direction. So there's my R vector. My F vector just points to the left, so that's just a negative I hat. So F is equal to -100.0 newtons in the I hat direction. So when I try to take torque is equal to the determinant of a matrix, then I write I hat, J hat, K hat, and then I write, of course, 2.00, 5.50, and then I write 0, and then I write -100, 0, 0. Obviously, when I do the I, that's 0 times 0. When I do the J, that's 0 times 0. So you get zeros for both those. When I finally get to the K, though, I do
see
0.
it.
Oh, thank you. So when I did the I, what was left was this times 0 minus 0 times 0. So that was 0, no I's. When I do J, I get 0 times negative 100, which is 0, and 2 times 0, which is 0. So no J's. But when I get to the K, I get 2 times 0, which is 0. And then I do minus negative 100 times 5.5. So that's 550.0 Newton meters in the K hat direction. Notice the minus with the minus here made it a positive, and that in fact points in the K direction. This is why I told you you have to use a right-handed coordinate system where I hat cross J hat gives you K hat, K points out. So K does point out of the page, and that's exactly the direction we got as well by our right-hand rule. So how's that? Does that make sense to you guys? You see how you can use a cross product to calculate a torque now? Easy peasy, right?
Yep.
All right, so now that we have that out of the way, I'm going to work a rather robust dynamics problem, and this is going to be like a very complex Atwood machine, and it takes more or less a whole sheet of paper. Actually, it takes more than a whole sheet of paper, so I'm not even going to try to start at the bottom of this page. So what I'm going to imagine is this. We have a small pulley, and the radius of that small pulley will be R, S, say. And attached to it, fixed to it so they don't rotate separately, they got to rotate together, is our B size pulley. Okay. Again, they're concentric, even though it doesn't look like that by this drawing. And in fact, I'm going to assume we know RS and RB. And in fact, we also know I, which is 1/2 MS RS squared plus 1/2 MB RB squared. So the B stands for big and the S stands for small. So I know the moment of inertia. I know the equation, the equivalent of Newton's second law is the summation of the torques is equal to I times alpha. Alpha has that sort of same right-hand rule direction sort of thing. But this is where you're not going to use the direction of it too much, except to remember that all of these have to be consistent. Now, in this RS, I'm going to hang from the smaller one, in other words, a big mass MB, or actually, I just call it big M. That way we don't have to have so many subscripts. So that's just a big M. And from this side, I'm going to hang a mass little m. Okay, I'm probably not going to use this formula at all. You can plug it in later. I'm just going to call it I every time, but I'm not going to use that. I just wanted to give you an idea that these are basic cylinders, and later I'm even going to do an integration problem where I can derive the moment of inertia using calculus and get that these are the formulas for cylinders. Okay.
What is I in this
I is called the moment of inertia.
Okay, that's right. Because I remember in the book it's P.
In our book.
Is it? It said I in mine.
That's weird. Oh, you might be thinking momentum.
Oh, okay. You're thinking moments.
Yeah, this is yeah, and this is quite a bit different from the moments that you're talking about in your statics class. I forgot exactly what they call it, but the thing that you do in dynamics, for instance, has this with like units of inches to the fourth or something god awful like that. That's what this quantity is. Okay, we call it the moment of inertia in physics, and it's really if it's a bunch of things together, it's M sub I R sub I squared, where you sum them all up. So M1 R1 squared plus M2 R2 squared plus M3 R3 squared, so on and so forth. R
You use some bizarre equations that we have to use find inertia statics.
Yeah, yeah, and yeah, and I think the inertia in there in that realm is different than this thing. But yeah,
Okay.
the equations are different. Part of the problem is they're using the same idea of moment of inertia, but they have to take out what material they're using. So the strengths of materials are dependent, for instance, on densities, and for instance, in the wood building industry, we use pine. Southern yellow pine is our strongest wood. Then we use just plain pine, or then we use spruce pine fir, which means you can get any of those. And then the International Forest Products Association sends out letters of what the values are for that. And to allow that to come out, you end up having to get rid of a DM, and it ends up becoming like basically DV, which is like DM over rho. So you end up getting like inches to the fifth or some god awful thing like that.
Yeah, that comes back in methods of materials later.
Yeah, yeah, and strength of materials. Yep, that's where you do the third order derivative to find the bend and all that good stuff, or deflection, I should say. So yeah, this is related. It's just like I said, we use a slightly different language here. We found it more useful. We call pressure. You guys call it head, that sort of thing. So what I'm going to do now is I'm going to do an Atwood machine like this, but in this case, there's some differences. Okay. This pulley having a mass means, let's assume this big mass is the one that moves. Again, that big mass is supposed to be just plain big M, not M with a B down there. I'm doing my best. There you go. Finally erase it. All right. So that's just that. Now, what this thing sees is it's trying to fall at a rate of 9.8 meters per second, but this rope is pulling back on it. So if you drew its free body diagram, you'd put a big M right here, and I'd call down the positive direction. So I'd say, here's my positive direction, like that. And then I'd say there's a vector right here whose magnitude is mg. And it has some other vector slowing it down, which the mass just says there's a rope slowing me down. And that's in the negative direction. So that's just T. And here's the weird part. I'm going to have to label it TL for the left-hand side. The reason why is because this tension here is going to result in a rotating of this whole disc. And then this disc over here is being attached to that pulley, is it's going to cause this one to have a tension. But this tension is just the tension required to lift this mass M, whereas this one was the one required to slow this mass M down and to rotate the pulley and to lift the mass. So these two tensions are in fact going to be different. That's why I had to call that TL. Now from that, I can get a free body diagram that is mg minus TL is equal to big M, and I'm going to call this A. Let's do AS for the small side. I could do AL, either one, but I'll do AS. I should have did this for S too. Yeah, let's call that S. That way we won't have a bunch of different subscripts, so I'll be the same subscripts and keep us a little more safe. So call that TS instead of TL. And just everything associated with the subscript S means it's attached to the small spindle or the small pulley. So that's our Newton's second law. And I'm going to call that equation 1. Now I'm going to draw the free body diagram for the mass little m. Now its mass is little m. Now, since we decided big M going down is a positive direction, that means little m going up is the same. So that's a positive direction. So in this case, we have a tension TB, which I would have called TR, right? I have a tension TB pulling up on it. That's in the same direction as big M going down. So I gave that a positive sign. And now I have a force that's slowing that mass down, namely its weight, and that force is little mg. So now with this equation, I get TB minus mg is equal to m. And again, I have to have a different acceleration because these radii are different. So I'm going to call that a b for the big side. Okay. And that's going to be equation 2. Now, let me explain a little bit what's going on there. Now, normally, like when we did the regular Atwood machine, it was one pulley And if this string went up an inch, this string would have to go down an inch. Well, this string could go up an inch, which might make this go through 30 degrees. But when this thing goes through 30 degrees, which it has to, if that one goes through 30 degrees, that's going to be a lot different distance than an inch. So that's why those two accelerations have to be different. So solving this problem introduces us to a lot more unknowns. We already don't know TS, we don't know TB, we don't know AS, and we don't know AB. So we're already up to 4 unknowns, and it doesn't get any better. So now let's draw a free body diagram for the pulleys. So for the pulleys, obviously not to scale, but maybe drawn a little better than that other piece of crap. Okay. So everything consistent with big M going down is supposed to be positive. So I'm going to say this torque on this side is going to cause a positive torque. And this is, of course, I should have drawn that this way. Oops, let me do that. This is going to be TS in the positive direction. And I'm going to have, of course, TB in the negative direction. And of course, this distance is RS. And this distance is RB. So Newton's second law, since these forces and lever arms are perpendicular, we get a nice, neat RS TS minus RB TB is equal to the moment of inertia of the pulley system, which I have written here, but we're not going to use it other than I, times alpha. So we've then introduced a fifth unknown. Okay. So the alpha is another unknown, and that's going to be equation 3. Okay. Now I like to practice good algebraic hygiene when I'm solving systems of equations. That's what I've recently coined that phrase. And what I mean by that is keep track of exactly what equations you're using and what you're doing to them. So if you ever find a mistake, you can correct it and see where it came in at and all that good stuff. And you can even make sure that you use all the equations, because if I have 5 unknowns, I have to use all 5 equations. Even if I seem to have gotten the answer before I use the 5th one, it can't be right. I have to have 5 equations to solve for 5 unknowns. Okay. So what we're wanting to know is what is AS, TS, AB, TB, and alpha. That's our questions. What we know is I, M, RS, RB, MS, and MB. Okay. So we need these things in terms of only these things. Now we've only got 3 equations here, but we got 5 unknowns. Well, the good news is there's a couple of things we know. We know that alpha, for instance, for this one and alpha for this one are identical. And we also know from, remember, S equals R times theta gave us V equals R times omega, and that gave us A equals R times alpha. Well, that tells us that, and I'm going to call this equation 4, but it's really equations 4 and 5, because I'm going to say alpha is equal to AS, that's the acceleration of the small disk, divided by RS, but it's also equal to AB over RB. Okay, so the fact that those two are equal is one equation. The fact that alpha is equal to either one is another equation. So it's really like 4 and 5 together. So I've actually got now 5 equations. Okay. So what I want to do is try to do like we did with the Atwood machine. With the Atwood machine, we were lucky in that this T and this T were negatives, but opposite. So we could just add these 2 equations and eliminate them. But now these 2 T's are different. So you can't just subtract them and expect anything. What I'm going to try to do is find this value and this value, plug it in here, and have this value and this value in terms of only one acceleration. So what I'll do is I'm going to solve equation 1 for TS, and then I'm going to multiply it by RS to get RSTS. So solve, this is my good hygiene I'm talking about, 1 for TS and multiply by RS. So clearly TS is equal to, when I pull that over there, that becomes positive. This one's going to come over here and be negative. So I'm going to say M times parentheses G minus AS. Now, when I multiply that by RS, it says RS is going to equal, or RS times TS, excuse me. RS times TS is going to be RS times M times parentheses G minus AS. Okay, I'm going to call this 1 prime. Now I'm going to solve 2 for TB and multiply by RB. So TB is equal to, notice the MG comes over here and it's going to be, both of them will be positive. So I'm just going to say it's M times G plus AB.
You can't see it.
Thank you. So TB is going to be M times G plus AB in parentheses. Now I need to multiply that by RB, and that's going to give me RB TB is equal to RB little mass times G plus AB. And that's going to be 2 prime. Okay. Now I've got basically one of my unknowns solved for only one unknown, and then other unknown solved for only one unknown. But if I could turn them both into the same unknown, then life would be great. And in fact, to do that, I'm going to say, let's let AS be replaced by AS is equal to RS over RB times AB. In other words, I'm eliminating AS and everything's going to be in terms of AB now. So when I do that, this is 4 prime. So 4 prime into, let's say, put it into 1 prime. And I'm going to get RS TS is equal to RS M times G minus RS over RB times AB. And that's going to be 1 double prime. So now what I have is TS only in terms of AB, and I have TB only in terms of AB. So that's really nice. In fact, if I could put these in this, I'd only have an unknown of AB and alpha, but there's a relationship between AB and alpha. So I can relate this alpha to AB as well. In fact, alpha is going to be AB over RB. So I'm going to take equation 3 for 1 prime, 2 prime, and 1 double prime. 3 for 1 double prime and 2 prime gives me RSTS. We see it right there, right? So RSTS, I'm going to write RSM times G minus RS over RB times AB minus RBTB. Well, RBTB is RB little m G plus AB. So that's the whole left-hand side of equation 3. Now I'm going to write the right-hand side, but instead of putting alpha, I'm going to use equation 4, which tells me alpha is AB over RB. So I'll put it over RB and call that AB. So now I have everything in terms of only one unknown, AB. In fact, it would be smart of me to multiply everything by RB. So I'm going to multiply both sides of this equation times RB times RB, and that's just going to make life a little simpler for me. So now I'm going to have, and I'm going to go ahead and distribute as well. So I'm going to say RSRB MG minus RSRB times RS over RB times AB times M. I should put the M before then, but I did it anyway. So now this one's going to be a RB squared. So I say minus RB squared MG minus plus becomes minus RB squared MAB. And over here, that just gets rid of that RB in the denominator. So that's just going to become I times AB. And in fact, I can get rid of this RB in the denominator as well by that. So now I'm going to group all the terms that have AB in it on one side so that I can solve for AB. So this one has an AB in it. This one has an AB in it. And this one has an AB in it. And that one's positive. So I'm going to pull all the ABs over to that side. And then what's left is this stuff. So I'm going to write this stuff first. That'll be RS. I'm going to put the M in front of it. RS RB times G. And then I'll say minus M in front of it again, RB squared times G. So that could hear that one and that one. All of this is going to be equal to I'm going to factor out the AB as I go. So I'm going to say just plain I. This one's going to come over here and be RB squared times M times AB. So it'll be plus M RB squared. Notice the little m is with the B for big. So that's what we had it. And then that takes care of that one. And now this one's going to come over here and it's going to be positive on that side as well. And it's going to be big M RS squared. So the big M's with the small radius. And all of that is times AB. So I now have AB is equal to M RS RB minus M RB squared over, notice I'm factoring out the G, over I plus M RB squared plus big M RS squared. All of that times G. So there's a unitless quantity multiplied by G. So you know the acceleration came out in the proper units because it has the same units as G. And that is our first answer. Not only that, we need to check it for consistency. For instance, with the Atwood machine, we found A was equal to M minus M over M plus M times G. And we found that tension was equal to 2M over M plus M times G. Well, check this out. Let's let I approach 0 and RA approach RB, which approaches just plain R. Then AB is going to become, notice this would be R squared, R squared, R squared, R squared. This I would go to 0, so it's not even going to be there. Those R squareds are all cancel out, and I get M minus M over M plus M times G. So that's a good check that our math came up to be the same thing we got in the special case of the regular Atwood machine. Pretty cool, huh? You always try to do that with your equations, try to make it look like something that you've done in the past so you can be more confident that you're right. If it doesn't work out to be the same thing, then you know you've done something wrong or your logic wasn't right in thinking they were the same. All right, now we know that A small is actually from equation 4. A small should be equal to R small over RB over R big times A big. So that means our A small should be, basically I just multiply by RS over RB. So this one's going to become MRS squared. This one's going to become, one of those RBs is going to cancel out and I get MRS RB. The denominator will stay exactly the same. That's I plus MRB squared plus big MRS squared. All that times G. And we got another answer. Again, if we let I go to 0 and the R's approach each other, we again get AS is equal to M minus M over M plus M times G. So you should be able to see that as well. Anybody not see that, or anybody need help seeing that? Pretty straightforward, right? All right, so now all we got to do is use these to find out what our actual tensions are. And of course, we can also use these to figure out what alpha is. So let me do the alpha first. Alpha is just AB over RB or AS over RS or whatever. So we know that alpha is equal to AB over RB, say. So I can go ahead and take my AB, which actually I'll bring over here so you can see it. You can see that one and this one at the same time. So alpha should just be equal to, and I'm going to write this kind of smartly. I'm going to take the AB, which you see there, and I'm going to divide it by RB. And what you can see is that would be M times RS minus M times RB over I plus MRB squared plus MRS squared. And all of that times G. And what I want you to call your attention to is notice the difference between this and this is basically G over a factor of R. So it's G without the meter part in it. So meters per second per second. The meters just canceled out because I divided by R. So it's just radians per second per second. So now we've got alpha. Now all we need is our tension left and our tension right. So if we use part of equation 1 prime, gave us that TS is equal to M times G minus AS. So T1 prime gave us that TS is equal to M times G minus AS. See right there, that was the step before we multiplied by R. So now all I have to do is do that. And that means I'm going to get a common denominator. So I'm going to write basically M times the denominator. So the denominator of AS is this I stuff. So I'm going to put an I M, and I'm going to pull the G out in front just like I did before. So remember the G was out here. So I'm just doing M times G actually, I like the way I started off that. That's going to be M times G minus M times AS. So that's going to be, this is where I get a common denominator. I'm going to take the I, multiply it by the M. I'm going to take the little m and multiply it by the big M. I'm going to take the big M and multiply it by the big M the square again. That's going to be the numerator of this. And then this one's a minus, and it's going to be the same original numerator that we had, but times big M. So I'm going to say big M times, we're doing AS now. So AS was big M RS squared minus little m RS RB. All of that times G, but also over the denominator, which was I plus M R B squared plus M R S squared. Whoa, got that reversed. Little m should be with RB. Ooh, that was close. And big M should be with RS. I don't know why I just copied it wrong. I knew exactly what it's supposed to be. But anyways, there it is. So that's the answer, but there's some simplifications that can come in here. For instance, you see, well, let's go ahead and distribute everything and then we'll see them. So I'm going to say TS is equal to IM plus MMRB squared plus M squared RS squared.
It's not on screen.
Thank you. There you go. So M squared RS squared is this guy. No, M squared RS squared is this guy because I'm on third term. Now I've got to do this M times MRS and the minus. So there's the minus, and then I got M squared RS squared, and then minus times a minus makes it a plus, and I got M big M RS RB. All of that over I plus MRB squared plus big M RS squared times G. Now you can see the cancellations. It looks like a M squared RS squared is negative here and it's positive there. So that's all that's really going to cancel out. But that's okay because now we got an answer. Our answer is T on the small spool, on the small pulley, is going to be I times big M plus M times big M times RB squared plus M times big M times RS RB over I plus MRB squared plus big M RS squared times G. And that's our final answer. Let's look at it in the limit that we were talking about earlier. As I approaches 0, keeping this in the way is a pain. I approaches 0 and RS approaches RB approaches just plain R. Then TL approaches, or TS, excuse me. TS is going to approach, the I is going to cancel out, or it's going to go to 0. So these two terms disappear. But notice this becomes R squared, R squared, R squared, R squared. All of those can cancel out. So I'll get MM plus MM. So that is in fact 2MMG over M plus M, which is exactly what we had for the tension in the Atwood machine. Okay. Now, one big hurrah for the last part, which is the tension big. So according to equation 2 prime, T big is supposed to equal M times G plus AB. So lowercase m times G plus AB, which is MG plus MAB. So I'm going to make this M, I'm going to get a common denominator with the AB, which is the I stuff right there. So I'm going to say I times little m. And remember, the G is going to be there as well, but I'll have that outside because the AB has a common G in it. So I times little m plus little m squared RB squared plus M big M R S squared. That looks good. Plus, now I have M times the numerator of AB, which is big M RS RB minus little m R B squared. All of that over I plus M RB squared plus big M RS squared times G. Now, once I distribute some of this stuff, I no longer need to look back at those equations. But once I distribute some of this stuff, I should get at least one nice little cancellation. So I'm going to say I M plus M squared RB squared plus M RS squared plus M RS RB minus M squared RB squared. All that over the same denominator times G. In this case, let's see what cancels out. I've got an M squared RB squared and a negative M squared RB squared. That's all that's going to cancel out.
You're off the camera again, Professor.
It keeps sliding down, but thank you. So TB, I'm in the camera again. So this gives me I times M plus M. And we could actually write it if we wanted to as RS squared plus RS RB. Whoa. All of that divided by I plus MRB squared plus big M R S squared times G. And you can see again that if you let the R's become equal and let the I's go to 0, you do in fact get 2 MM over M plus M. Any questions on that? All right, any questions on that whole rigmarole, like how we did it and all that good stuff? Notice the biggest part of this was solving a system of 5 equations, 5 unknowns, and all I really did was just try to make sure I did that in a reasonable, straightforward, thought-oriented, strategic way. So I recognized what my unknowns were. I made sure I had an equation for each of the unknowns, because you have to have, one equation for every unknown. And then I methodically looked for a way to eliminate unknowns. So what I was trying to do was eliminate TS and TB by solving 1 and 2 for TS and TB, and they would be in terms of 2 different accelerations. But I knew I could relate those 2 accelerations. So then I'd have TS and TB in terms of 1 common acceleration. I could put that in there, and I'd have this whole left side in terms of 1 unknown. But then that alpha, I could relate that to that same unknown. So I did that, and that got it down to where I had only 1 unknown and I was able to solve for AB. And then of course I could just use my relationships to get AS, to get alpha, and to get TS and TB. And of course I always check them, as is good to do, against things I already knew, just to make sure that they made some sense. So that's sort of like a holy grail type problem, meaning if you can do that symbolically, you're in a really good place in preparing for your tests and that sort of thing. If on the other hand you can't, but you can do it numerically, then you're also in a good place. And that's what you want to be able to do, is you want to be able to do it numerically. And then after you get the hang of it, you might be able to do it symbolically. And then you're a little bit more efficient of a physicist. I literally one time had a friend of mine, I was working in trying to get into structural engineering. I was just doing wastewater at the time. And the person that I wanted to work under for structural engineering knew a lot about structural engineering, but he was calculating something for a flitch plate. And basically he was calculating the same thing that I was just talking to you about, that inertia thing that comes out to inches to the fourth. There's a formula you can use that you do it if you, a flitch plate is basically like you take a 2x10 or a 2x12 and you sandwich a piece of steel in between it, between two of them, and then you calculate the net strength of the two. And in fact, if you do a what we call an engineered beam, which is really nice, you can actually take a 2x10 and put it on top of a 2x12, and then put a sheet of plywood through the middle, and then put a 2x10 and a 2x12 on top of each other, and then screw them and nail them all together really good and glue them all together. And that gets an engineered beam that we use in structural engineering. But if you calculate that moment of inertia, which tells you how much deflection it gets, if you calculate it one way by adding things up, you get one answer. If you calculate it another way by just taking sort of the sum of what they are as opposed to the sum of the parts, then you get a different answer. And the engineer came to me and said, maybe you can help me figure this out. You seem to be pretty good at math. I was like, yeah. He said, when I do it this way and I do it this way, I get these two different answers. I said, I guess those answers are off. And I gave him the number off the top of my head because I was pretty good at arithmetic at the time. And he said, how the hell did you know that? Well, what it was basically the equivalent of, if you work this out symbolically, when you take a plus b squared, one way he was calling that a squared plus b squared. And the other way he was actually doing it more correctly, which was a squared plus 2ab plus b squared. And he just didn't realize that's what he was doing because he's just doing it all in numbers and didn't really see the gravity of the situation. So I calculated the 2AB for him and told him that's how much he's off. And he said, damn, you're right. And that, of course, got me into structural engineering immediately because he was so happy to have someone that could help him. He was the only one doing structures at the time. So I did get into that. And then I left the company and went to another one. But all of that was because I could do things symbolically. So it's really, really powerful to do it symbolically. One of the first things I did when I got into doing structural engineering is I calculated the slopes of various 10-12, 8-12, 9-12 roofs, and then the hip angles and then the valley angles and all that stuff. And I did them arbitrarily and symbolically. So I could just plot, take whether it's a 9-12 or a 10-12 or 11-12, I just stick in the 9, the 10, or the 11 and immediately have all my answers just because I could do that symbolically. So I do recommend you do that. That's what you're starting to work out in, hopefully, in the calculus-based physics sequence. In the algebra-based sequence, you hardly ever do that. You always just go with numbers. But what I want you to do is always feel free to just go straight to numbers. If the algebra gets too complicated or you're afraid you're going to get lost, then by all means use the thing you're comfortable with, but try to reach for getting that algebraic sense. It'll help you in your fields in the future. Let me now show you, we've got about 8 minutes left. I want to show you another type of rotational motion problem. And this one's kind of interesting, but and it pertains to everyday life. That was example, I think 4. I can find that.
I want to say it was number 3.
Yeah, that was 3. Thank you. So this is example 4. I didn't even number it. That's why. So this is example 4. So example 4 is going to be basically a long, thin rod. Here I am symbolically again, of length L, and it's uniform.
Is the screen supposed to be up?
Oh, thank you. Y'all don't like looking at the top of my head? What's wrong with you? Yeah, you should probably be looking at the computer screen at this point. I mean, at the actual paper at this point. So let's imagine it could be like a smokestack. Have you ever seen like a chimney being knocked over or something like that? When they go to fall, they usually break in half and then fall. And I'm going to show you why. Okay. So what we're going to do is imagine it's on a hinge right there, and it has a mass big M, and it's uniformly distributed. And what that means is basically there exists a constant lambda equal to dm over dl. Now in practice, when we're doing this, we're going to have our dm's from, remember, I equals the integral of r squared dm. We're going to have the dm either equal to lambda dl, and that lambda doesn't have to be a constant. In this case, it is, because it's uniform, or it'll be sigma times dA, where that's a mass per unit area. This is a mass per unit length. Or it'll be a rho dV, where that's a mass per unit volume. And again, these can be constant. If they're said to be uniform, they will be constant. But if they're not said to be uniform, then they might have a value like some constant times x squared, or some constant times x sine theta, or some weird stuff like that. So in this case, I'm going to have to actually calculate that. So what I'm going to do is I'm going to imagine this thing has now begun to tilt, and it's very thin and very long. Okay, so let's say right now it's at an angle theta, and right here is the center of mass. So this is up a distance L over 2. That's why I told you it was uniform. Okay, so if I want to draw this object, I'll draw a free body diagram like this, where basically I'm showing a force, big M G, pointing down on it. This is the angle theta. This is L over 2 right there. Okay. So I could take the component of torque that is, well, I could calculate the torque. Remember, torque is equal to many different things. It can be R perpendicular times F, or it can be F perpendicular times R. In this case, I see a component of R that is perpendicular to mg. So R perp is actually equal to L over 2 times the cosine of theta. Everybody see that? So I can say the torque acting on it is in fact M, let's say 1/2 L mg cosine theta is the torque acting on it. Okay, so the 1/2 L is the lever arm, or the 1/2 L times cosine theta is the R perp of the lever arm, and then mg is the force. So that's where that all came into. Well, that has to be equal to, because that's the only torque acting. The other force that's acting is acting here on the ground, and that doesn't help us any because that has 0 lever arm. So that has to be equal to the I of the beam times alpha. Okay. Now, the problem is we need the I of the beam. Well, the I of the beam, I, is equal to the integral of r squared dm. Well, what I'm going to imagine is this long rod of length L along the x-axis, and I'm going to choose a dm right here. That dm is going to be equal to lambda dx, and that lambda, of course, we already figured out was m over L. And then I'm going to say I is equal to the integral of x squared, because the distance from here to here is really x. That's what our R is. And because it's thin, there's not much difference between R here and R here and R here. Okay, that's why I said it was very, very tall and thin. So I got x squared times m over L, that's the lambda, times dx, and I'm going to integrate from 0 to L. And lo and behold, I'm going to get m over L times 1/3 L cubed. Because the integral of x squared dx is 1/3 x cubed, right? So now you see that I get 1/3 ml squared is the moment of inertia. So now I can put 1/2 LmG cosine theta is equal to 1/3 ml squared times alpha. But alpha, remember, is given by A is equal to R times alpha. Well, the R in this case is just plain L over 2. So alpha is going to be 2A over R. So I could leave it that way, or I could just calculate it as alpha. Either way, doesn't matter. Now you can notice that the L on this side, one of them is going to cancel out. And the L on this side, one of those is going to cancel out. And the M's are going to cancel out. So it's actually independent of the mass. And what you end up getting is that alpha is equal to, we're going to have G cosine theta over, or 3G cosine theta over 2 times L. So that's what our acceleration is. Notice that has units of meters per second divided by meters. So that's just radians per second per second. So that's the angular acceleration it's going to reach. The acceleration of the actual center of mass is just equal to L over 2 times alpha. So I can now say 3/4 G cosine theta is the linear acceleration. And that's of the center of mass. But check this out. The linear acceleration of the tip, let's take the top so we won't be confused because it goes another L over 2 out here, is just equal to L times alpha. So in that case, it's going to be, in fact, 3/2 of G times the cosine theta. And when, of course, theta is equal to 90 degrees, you get 0. But when theta is equal to 0 degrees, you get 1. So you can see as it's approaching the ground, it's not accelerating. The tip's not accelerating at G. It's accelerating at 3/2 G, 1.5 times G. So that's the danger of falling trees and falling smokestacks and stuff like that. If you're used to seeing things fall at 9.8 meters per second, you might not move fast enough to get out of the way of this thing because gravity's pulling on the center of mass and only the center of mass is moving at the G rate. When you actually get to the tip, that's actually moving twice as fast if it's a uniform body. So that's all I wanted to do with that. Notice I also did slip in a derivation of I for a particular body. If you now reverse that and put it at negative L over 2 and positive L over 2, you'll see that you can get 1/12 ml squared. Both of those are in the manual. And next time I'll show you that and I'll show you the cylinder. The center of mass, or excuse me, the moment of inertia for a cylinder. You guys are free to go. I will wait around for the last person to ask questions. And I know one student had a question they want to ask after class, and we can go into a breakout room if you need privacy, but I'm going to stop recording when we get to his question. Anybody have any questions on anything else?
I had a question about the midterm. Did they ever send you the formula sheet?
Yeah, I got an email from them.
Okay, you did. Good.
Yeah. Yeah, it's all taken care of.
All right, that's good. And I had one more question. I'm trying to sign up for the physics 2 for next semester.
And did it not let you the 242?
Because I haven't completed this class yet. It says like you need a permission number or something. I was wondering what to do about that because I don't want it to get filled up before I can sign up for it.
Actually, that's the Chesapeake campus. It's for Mr. Mitchell, right?
Yes, sir.
Okay, that is a wonderful class, but as far as I know, we are not, regular students are not allowed to enroll in that. The shipyard pays us personally to train their students there. And not only is it all just shipyard students, but it's all the way in Suffolk over just at the foot of the bridge going over to North Shipco. So it's not even at the Chesapeake campus, it's all the way over there. So yeah, we got very slim pickings this semester because we have so few faculty left. We've got a one faculty member that went out on maternity leave, and she's still trying to work half-time just to help us out. So we're really short staffed. That's why we didn't have much more to offer. I think I'm offering the only 242 section other than that one.
Oh, okay. All right. Well, thank you. That makes sense.
No problem. Sorry about that.
Thank you.
I'm trying to double check to make sure I'm correct about that, but I'm about 99.9% sure that the shipyard class can't be taken by anybody else.
Would it be possible to have like a permission number to sign up for your class next semester then?
Yeah, you
Professor?
should. You shouldn't ask you for permission for that one. You should just go.
Okay.
Yeah,
All right. Thank you.
no problem. Christian, David, or the other David, or Nathaniel, anybody else have any questions? Noah?
I was just listening to other people's questions.
Okay. Sam said you're gonna wait for other people's questions. That was you, right, Sam?
Oh, I just had, I wanted to I noticed something in the calculations of the last example. I just wanted to throw it your way and see if I was along
Okay.
the right track.
You talking about the midterm?
Oh, no, on the falling tall thin thing.
Oh, okay, gotcha. Yeah.
It's interesting because if you treat the center of mass as a fixed point and then the top as another fixed point, like those are where the masses are centered.
Right.
It makes sense that the top falls faster because when you think about it, if the force of gravity is acting at the center specifically, it almost acts like a launching arm. Like there's a force of leverage at the center of mass that accelerates the
end.
top.
Yeah, like a trebuchet or something like that.
Mhm.
Yep. And that's also, I recognize that from water skiing. If you've ever been a water skier, you know that a water skier can follow a boat going 30 in a curve, but the water skier can go out on the end of the rope and swing out beside the boat and be moving at, 60, 65 miles per hour, even though the boat's only going 30. So yeah, that's the same sort of thing. It's good that you're noticing that. That's the way physicists and engineers need to think. So good job.
Thanks. Sorry, my cat's yelling at me.
Mine hasn't started yet. She'll be in here in a second. Anybody else have any questions?
Yeah, I'd like to speak to you privately.
No problem. I'm going to go ahead and open up a breakout room. If anybody else has any questions y'all want to wait for, just wait here and I'll come right back. If not, you can go ahead and
Okay.
split.
I'll wait.
Okay. Let's see.
See you Thursday,
Great.
Professor.
And is Christian that needs to, you too, is it Christian that needs to speak privately with me?
Yes, sir.
Okay. I'll be right back, Tristan. All right, what's that? Hold on a second, please.